Okay, welcome to lesson 28. We're getting toward the end of module 4. And in this lesson, we're going to learn another method for solving a linear system using algebra. Because we saw in the last lesson that graphing is great for estimating, and for certain systems, you can read the exact solution off of a graph. But for many systems, the graph will only get you close. It will not give you an exact solution. So we need to use algebra. Plus, it's faster and easier. So we want to develop some more algebraic methods for solving linear systems. So let's look at, let's kind of recap what we've done so far. Okay, so there's 3 systems here. And think about how you would solve these systems algebraically, because there's always, even though we could use one algebraic method for every system, certain systems lend themselves to be more efficient one way or another. So look at these 3, pause the video, and think about what would your first step be to solving these. And these are all examples from the last lesson. Okay, so let's just take each one separately. So for the first system here, the first set of equations, they're in the form, they're in slope-intercept form, right? They're both y equals an expression. Y equals this expression. So in my linear system, remember, the y's in my solution will be equal to one another, because that's what I'm looking for. I'm looking for the one point that is the intersection of these 2 lines. So what I can do for this one is I can say, since both of these things are equal to y, then they're equal to each other. So I can say that 3x plus 5 is equal to 8x plus 3. And I've eliminated y from the system now. And so I can solve for x, and I can go through the steps and find that x is equal to some number. When I get that number, that's going to be the x-coordinate of my solution, and I can plug it into either of those equations to find the y-coordinate. Okay, so that works really well because they're both in the form of y equals something. Okay, let's look at the second one. This one, the first one says y equals some expression. The second one is 2y is minus 4x is equal to 10. Okay, so it's not in the form y equals some expression. So I could do some algebra and put it in that form, or I could do something a little more straightforward, which is to say that since y is equal to 7x minus 2, I can just put that in for y in the second equation and eliminate y by doing that. So what would that look like? That would look like this. I'm going to rewrite this second equation, 2 times y minus 4x equals 10. And instead of putting y in there this time, I'm going to put 7x minus 2, because that's another expression for y in my system. And it will be true in both equations. So notice now this equation here now just has one variable that I can solve for. So I can do the same thing as I did in the first. I can get x and then come back over here, plug my number, my solution for x in here, and solve for y. And we found that it didn't matter which equation we chose to put the x in, it would be the same for both of them if I've done the math right. Okay, let's look at the third one. So in this one, these are not in slope-intercept form. They're kind of the opposite of that, right? They have x equals some expression, and the second one is x equals some expression. So because that's true, the quickest thing for me to do in this one is to eliminate x. So I'm going to eliminate x by saying that since x is equal to both of these expressions, then these expressions have to be equal to one another. So this is 10y plus 2. And this time I'm going to get y equals some number, and then I'm going to go back and put y in to find my x. So just make sure when you do one like this that you get your ordered pair in the right order. Okay, so that's kind of a recap of what the methods kind of that we used in the last lesson. So we're going to look at these numeric examples. Notice in all these examples here, there's no variables. Okay, we're just using numbers to show something that's true. Okay, so what I want you to do is pause the video and look for a pattern in the following examples. What is happening in the following examples, and see if you can find the pattern here. Okay, so hopefully you noticed some things. Let me get a contrasting color here. So if I see that these two expressions, 2 plus 5 and 7, are equal, and 1 plus 9 and 10 are equivalent expressions. Let's get some green over here. So 2 plus 5 equals 7, 1 plus 9 equals 10. Then if I add 2 plus 5 and 1 plus 9, that should equal my 7 plus 10 right here. Okay, so what I found is that if I have these equivalent expressions, I'm saying that 2 plus 5 is equivalent to 7. I've got the equal sign in between to show it. 1 plus 9 is equal to 10. Then if I want to add the left-hand sides of those two equations, they're going to have to be equal to the sum of the right-hand side of the equations. Now this seems really obvious with numbers, not as obvious when there's variables in there, but we're going to see how it works. Okay, so in this next one, same thing, right? I've got these left-hand sides here, 1 plus 5 and 7 minus 2, and down here 1 plus 5 and 7 minus 2. I've added those together, and they're going to equal the sum of the right-hand sides. Equals 6 plus 5. 6 plus 5. Okay, so the difference between the first example and the second example is that there's some subtraction going on here, but it still works, right? 1 plus 5 is 6, 7 minus 2 is 5, add them together, I get 6 plus 5, or 11. Okay, and then in this next example here, I've even got a negative number here. Negative 3 plus 11 is 8. 2 plus 1 is 3. I can add the left-hand sides. Negative 3 plus 11 and 2 plus 1 are right here. And then my right-hand sides, the 8 and the 3, they're equal. Okay, and that's just because I'm adding these equivalent expressions together. It's kind of a substitution sort of thing, if you think about it. So I want you to, it's always a good strategy to look for patterns in simple equations that we can understand before we apply them to slightly more complicated ones. So if you're not quite getting this, I'd like you to continue studying it for a little bit until it kind of sinks in. And then we'll go work on example 1. Okay, so example 1 says use what you noticed about adding equivalent expressions, and that's what we did here, to solve the following system by elimination. Okay, so what we want to do again, like we saw in the opening screen, is we want to eliminate one of the variables so that we can solve for one of the coordinates, either x or y, doesn't matter, and then substitute it back in to find the other one. So let's look here. So what did we notice? Well, we noticed that we can add the left-hand sides together, and that it's equal to the sum of the right-hand sides of equations, because these are equations, they're balanced. The left-hand side is equivalent to the right-hand side. So let's do that. So we've got 6x minus 5y, and I'll put parentheses around it for now just so we can see that, plus 2x plus 5y, and that is equal to the sum of the right-hand side, which would be 21 plus a negative 5. Okay, well, why do I want to do that? Well, notice that something happens when I do that, because I've got a negative 5y here and a positive 5y here. So when I simplify the left-hand side, which I'm going to do right now, when I simplify it, the y's are going to disappear, and I'll just have 6x plus 2x is equal to 21 plus negative 5, which would be 16. Okay, so continuing to simplify that, I'm going to get 8x equals 16 and x equals 2. So the x coordinate of my solution is 2. And so now all I'm left to do is to find the y coordinate. And I can do that by substituting. So let's get another color so we can segregate it here. So I'm going to use, I'll use the first equation. So I have 6x minus 5y is equal to 21, and x is 2, so 6 times 2 is 12 minus 5y equals 21, and so negative 5y, I'm subtracting 12 from both sides, so 21 minus 12 is going to be 9. And so y is equal to negative 5 ninths. Okay, hopefully you're screaming at me right now, because that's not right, is it? Go the whole way, Mrs. Hanson. All right, so dividing by negative 5, I'm going to get y, whoops, I still have my eraser on. I'm going to get y is equal to negative 9/5. 5 is in the denominator, not the numerator. Okay, so our solution here, now that we've solved for y, is negative 9/5 for the y coordinate. So this ordered pair right here, 2 and negative 9/5, should be a solution for both of these equations at the same time. So a good check on whether I got this right or not would be to look at the graph, to make the graph, and you'll be doing that in most of the exercises. So we said our solution was x is 2, y is negative 9/5. And so if we look at the graphs, these have been already graphed for us. Here's the graph of 6x minus 5y is 21, 2x plus 5y is negative 5. So the x coordinate of our solution is 2, and the y coordinate is getting close to negative 2, and negative 9/5 is just shy of negative 2. So our solution, our algebraic solution matches our graph solution, our solution by graphing. But notice we would not have been able to read negative 9/5 directly off of this graph. And if I had kept my negative 5/9, which is just a little over 1/2, that would have been down here, I would have noticed on the graph that I got it wrong. So I could have gone back and fixed it. So graphing is a good way to double check, but it doesn't have to be super accurate. So we'll see that in some of the examples. Okay. Okay, now let's look at example 2, and we're also asked to solve this system by elimination. And if you look at these two equations, if you think about adding the right-hand sides or the left-hand sides together and setting it equal to the sum of the left-hand sides, or whatever, the two sides, notice that there's no variable that's going to get eliminated, because when I add the x terms, they don't have the, negative 2 plus 4 is going to be 2. 7 plus negative 2 is going to be 5. So neither x or y is going to be eliminated when I add those together. So I have to do something else first. So what I'm going to do first is I'm going to get an equivalent equation. And if I take and multiply the first equation, both sides, by 2, and I'm doing that because I want to get the opposite of 4, you'll see in a minute. So I'm going to take 2 times negative 2x plus 7y. And I'm going to say that that's equal to 2 times 5. So I've just multiplied the first equation by 2, and I know that when I do that, I get the exact same line, right? So this equation becomes negative 4x plus, common mistake here, forget to multiply the second term by 2 as well. So this is going to be plus 14y is equal to 10. Okay, so this equation is equivalent to that one right there. And so I've still got my equation 4x minus 2y is equal to 14. So I have this new system here, which is the exact same system. It has the same solution. And I'm going to add these together. So I'm going to get negative 4x plus 14y plus 4x minus 2y is equal to 10 plus 14. And when I simplify that, these two terms become 0. They're opposites of each other, so they drop out. I can combine these two terms and get 14y minus 2y, which is 12y, is equal to 24. And so my y-coordinate of this system of equations is 2, because dividing by 12, y equals 2. Okay, so let's get started here. My y-coordinate is 2. Okay, don't put it for the x. We've solved for y now. So now we want to go back and see what x would be. And we can do that again by choosing either equation to do that. So I think I'll choose the second one. So I've got 4x, let's get a different color here so you can see what we're doing. I've got 4x minus 2y is equal to 14. I know y is 2, so I've got 4x minus 2 times 2, which is 4, is equal to 14. I'm going to add 4 to both sides, so I know that 4x is equal to 18. And so x is equal to 18 fourths, or 18 divided by 4, which I'm going to go ahead and simplify to 9 over 2, dividing top and bottom by 2. So the solution to this system is 9 halves, which is 4 1/2, and for the x-coordinate, and y is 2. So let's look at the graph of these two equations and compare it to our solution here. Okay, so the solution is repeated here, 9/2, 2. So let's look at the coordinates of that. So the x-coordinate appears to be at about 4.5, and the y-coordinate is 2. So the coordinates of that point on the graphs is the same as what we got solving it algebraically. Okay, so that's pretty cool. I think it's a little quicker to solve by using algebra than to solve by sketching the graphs. But we're going to continue doing both just so we can see that it's the same thing. Okay, let's look at this next one. This next one is even more different here. Got 7x minus 5y is -2. 3x minus 3y is 7. And I noticed that if I add them together, nothing's going to be eliminated because 7 plus 3 is 10, and -5 plus -3 is -8. So that's not going to get me anywhere. I could do it, but it's not going to get me anywhere. So I need to multiply. I need to get equivalent equations so that one of the variables will be eliminated. And so there's a couple different ways I could do this one. And what I'm going to do is I'm going to multiply and see if you can see what I'm doing here. I'll explain it afterwards. I'm going to multiply the first equation by -3. And so I'm going to have -3 times 7x minus 5y is equal to -3 times -2. And then the second equation, I'm going to multiply by 7. So I'm going to have 7 times 3x minus 3y is equal to 7 times 7. All right, so let's simplify the next step. I'm going to have -21x plus 15y. Notice -3 times -5 is positive 15. And then that's equal to -3 times -2, or positive 6. And then over here, I'm going to have 21x minus 21y is equal to 49. Okay, so I've got a whole new system here. I've got this equation and this equation, but this system's going to have the exact same solution as this system because they're equivalent equations, right? They're just multiples of one another. And I like this system better because notice I have the -21x and the positive 21x, and when I add them together, the x's are going to be eliminated. Okay, so I end up with, what do I end up with? -21x plus 15y, and then plus 21x minus 21y is equal to, do it in order, 6 plus 49. Okay, so I added the left-hand sides and said that that's got to be equal to the sum of the right-hand sides. So this is nice because now I've eliminated the x terms, and so I can simplify it with the y. So 15 plus -21 is going to be -6y. And I know that that's equal to 6 plus 49, which is 55. So dividing through by -6, I'm going to get y is equal to -55, 6. Okay, I would never be able to read that solution off a graph. And so I have negative 55 over 6 for the y coordinate of my solution. And then I would need to go back and find the x coordinate. Okay, so let's look, when you were looking at this one, maybe you thought, well, I could do it a different way, and you're absolutely correct. If we start over, looking at this fresh, and say, well, what if we wanted to eliminate the y variable? What would we do? Because by multiplying by 3 and 7, we eliminated the x variable. So try and do this again. Maybe pause the video and eliminate the y variable. Okay. Okay, so to eliminate the y variable, let's look at this. I get 7x minus 5y is equal to negative 2. And I've got 3x minus 3y is equal to 7. So I want to get the coefficients of the y terms to be opposites of one another. So I'm going to multiply the first equation by negative 3, and a negative 3 out here. And then the second equation, I'll just multiply by 5, and that way I'll have, multiply this by 5, that way I'll have negative 3 times negative 5 will be positive 15, 5 times negative 3 will be negative 15, and that will eliminate those variables. So this becomes, let's use a different color because it's getting kind of crowded in here. So this will be negative 21x plus 15y is equal to 6. And this equation down here will be 15x minus 15y is equal to 35. So again, these new equations here are going to have the same solution as our original equations, but but they allow me to eliminate a variable. So if I add these two together, I'm going to get negative 21x plus 15y, and then plus 15x minus 15y. That's going to equal 6 plus 35. And so I end up with a simplified equation with one variable that's going to be negative 6x is equal to negative 6x is equal to 41. And so x would be equal to negative 41 divided by 6. Okay, and again, I'd come up here, and this would give me negative 41 6. This would give me the x coordinate of my solution, and actually I already had the y coordinate, which was negative 55 6. But I don't have to do both of those, because what I would do with this is then come back in and put it up in one of these equations, and out would pop my negative 55 6 solution. Okay, we're not going to look at that in the interest of time, but you could do that. Okay, so let's go ahead and look at the exercises 1 through 3 that you have here, and you can work on those independently and then come back and check the video for your results. And then toward the end of this video, we're going to have a quick discussion about what are the simplest methods, because we're always wanting to find the simplest way of solving these systems. There are lots and lots of ways, but we want to be able to recognize the simplest way. Okay, so work on exercises 1 through 3, pause the video, and then come back to check your solutions and for solving, or for a quick discussion. Okay, for each of these you're going to need graph paper because you're going to be graphing these systems just to check your solution. Okay, so hopefully you've been working on these by yourself, and I notice in this one that if I just simply add the two, the left-hand sides, I'll get 6x minus 7y plus 3x plus 7y is equal to negative 10, negative 10 plus negative 8. I was getting ahead of myself there. Okay, and so I did that straight off because I noticed that the coefficients of the y terms were opposites of one another, so they're going to be eliminated when I add these together. So I'm going to get 9x is equal to negative 18, and x is equal to negative 2. So I've got the x coordinate of my solution to this system. So if x is negative 2, I can choose either equation, and I'll choose the second one. 3x plus 7y is equal to negative 8. I'm going to put in negative 2. I'm going to insert right in here. So 3 times negative 2 and I'm just doing this silently just so you can watch. So I'm going to add 6 to both sides. So I'm going to get 7y is equal to negative 2. Negative 8 plus 6 is negative 2. And y is equal to negative 2 sevenths. So negative 2 sevenths is my y coordinate of the solution. And so what we want to do now is look at the graph, and we want to solve that by graphing. A lot of these equations in this topic don't graph real nicely. Like, it's hard to find nice ordered pairs for them. So we're just gonna do it roughly. So let's look at making a table for both of these. So for the first equation, let's do an xy table, and we're just going to find the intercepts, okay? So if x is 0 in this first equation here, if x is 0, I have negative 7y equals negative 10. So y is equal to 10 sevenths. 10 sevenths, okay? Which is 1 and 3 sevenths, pretty close to 1 1/2. This is going to be a real rough graph. Now I'm going to make y equal to 0, and if y is equal to 0 here, then 6x equals negative 10, and x would be negative 10 over 6. Negative 10 over 6, which actually simplifies to negative 5/3. So I could do that, or I can leave it how it is. So let's graph that one. So the first point is going to be, let me get, the first point is going to be at about 1 1/2. X is 0. The y-intercept is about 1 1/2. So that'd be about right there. Okay, and now the x-intercept right here is negative 10 sixths. Negative 10 sixths is negative, negative 5/3, right? So that's negative 1 and 2/3, almost negative 2. On our graph, we're going to get that in there about right there. So then I can draw this line through those 2 points. So we're graphing by intercepts, right? Especially when these are written in standard form. That's usually the easiest way to go. So for this next equation, let's make an XY table over here. And let's get the y-intercept first by choosing x to be 0. So if x is 0, then I have 3 times 0 is 0. 7y equals negative 8. So y equals negative 8 over 7, which is a little more than negative 1. Let's plot that point. The y-intercept, about right there. And then the x-intercept, I want to see where that goes, is the point where y equals 0. So in the second equation, when y equals 0, 7 times 0 is 0. 3x is negative 8. X is negative 8/3, which is negative 2 and 2/3. So almost negative 3 over there. So where's that? About right there. And I can draw the line between those 2 points pretty roughly. Now, let's check and see. Our solution, we said, was supposed to be negative 2, negative 2/7. And so let's kind of analyze this. So here's the point of intersection, is right about negative 2, roughly. And the y-coordinate, negative 2/7, looks about right too. It's less than negative 1/2, so it's right there. So our graphs confirm our algebraic solution here. Okay, let's check exercise 2. All right, so for exercise 2, I went ahead and multiplied the first equation by negative 5 so that I could eliminate the x variable. So negative 5 like that. And so I'll quickly show you the steps here. Okay, so after multiplying through by negative 5, that's not a 2, that should be a 20 right there, 20y. Multiplying through by negative 5, let's make sure I don't make any other mistakes here. That looks good, negative 5 times 7. Then I went ahead and added this left-hand side and this left-hand side and got that. And then I added negative 35 and 6 and got that. And so when we eliminate our variable, we're going to get 29y is equal to negative 29. So y is equal to negative 1. That's nice. Finally have a whole number instead of a fraction. But we want you to, I want you to know that just because you get a fraction doesn't mean you got it wrong. These don't always come out nice. Okay, so if y is negative 1, I can take that back up into this first equation here, which is the simplest, and that's why I'm going to use it. X minus 4 times y, which is negative 1, is equal to 7. So x minus 4 times negative 1 would be minus a negative 4 is 7. So x plus 4 equals 7. Subtracting 4, I'm going to get x equals 3. So my solution is x equals 3, y equals negative 1. And that's the solution to this equation. Now, we could have done this a different way, but honestly, I think because this x has a coefficient of 1, that allows us to simply multiply to get the -5 here. And that's got to be our quickest route to a solution. But if you did something different and got the same one, then that's okay. So 3, -1. So let's look and see how, I'm going to write down 3, -1, which is, let's see, 3, -1. Our intersection should end up being about right there at 3, -1. And so let's check that and see how we do. Okay. So I'm going to do the same thing I did before, which is to find the intercepts and graph it. So I'm going to do that off video so you can do this quickly here. So pause it and do it yourself if you haven't already. Okay, so these two tables show the x and y intercepts for these two equations. So this first one here is to the first equation, the second one is for the second equation, and you can check that, check those numbers yourself. So let's graph them. Okay, here's what the graph looks like. So I plotted the x and y intercepts. This would be, this equation right here is the, which one? 2/3, and it's the second one. So this one is 5x plus 9y equals 6. And this graph right here is the x minus 4y is equal to 7. And this is the system. And so I've graphed the x and y intercepts here and drawn the line. And then I graphed the x and y intercepts for the other equation and drew the line. And they intersect right here at our solution 3, -1. Okay, let's do another one, another exercise here. Number 3. Okay, so this one, there's not, I can't just multiply one equation, so I'm going to have to multiply 2. So there's, you know, it's your choice on which variable you want to eliminate. So I'm going to, because the y variables already have opposite signs, I'm going to go ahead and eliminate that one. So I'm going to multiply the first equation by 5. And that's going to give me -15y. So 5 times 2x minus 3y is equal to 5 times -5. And then the second equation, so let's do that. That gives me 10x minus 15y is equal to -25. And then for the second equation, I need to multiply it by 3 to get the 15y. So 3 times 3x plus 5y is equal to 3 times 1. And I get 9x plus 15y is equal to 3. So I've got these two new equations here that I can combine and eliminate the y term. So these two new equations are going to have the same solution as the original equations because they're going to graph as the same lines. So when I combine those two equations, what do I get? I'm going to get 19x, and I'm eliminating a few steps here to make it go a little faster. I'm going to get 19x is equal to, and then I have to add the right-hand sides here. -25 plus 3 is going to be -22. And so x is equal to -22 over 19. So that will be the x coordinate, -22 over 19 of my solution. All right, so then I can come back up to one of the original equations and put that in for x and solve for y. So I'm going to choose the second one. So 3 times negative 22 over 19, 3x, plus 5y is equal to 1. So can't simplify anything here, so this is going to be negative 66 over 19 plus 5y equals 1. I'm going to add 66 over 19 to get rid of it. So I'm going to get 5y is equal to 66 over 19 plus 1, which I'm going to write as 19 over 19. And that gives me that 5y is equal to 85 over 19. And now I'm going to multiply by 1/5. 1/5. And I'm going to get y is equal to, and I want to do 85 divided by 5. I need to know how many are in there, and it's going to be 17 19s. Yeah, so basically I did that and got 17 up here. So y is 17 19ths. So that's the y coordinate of my solution right there. Okay, so that one's kind of ugly, but you can see, you can estimate what those numbers are. That's a little over -1, right? -1 and then some. And 17 19ths is just shy of 1. So that's where those two lines should intersect. Okay, so I'm going to talk you through how I quickly did this graph. I decided with this one that I wanted to put each of these equations into slope-intercept form so I could just graph the y-intercept and then count off the slope. So the first equation is this orange line here, the 2x minus 3y equals -5. Here's the y-intercept version of that line, and then the second one, here's the y-intercept version of that line. And so for this one, the y-intercept here is positive 5/3, so just shy of 2. And then I counted off over 3 and up 2 to get this positive 2/3 slope right here and graphed it. And then the second one, the y-intercept is 1/5, so right down here. And the slope is -3/5. So I went, to get the next point, I just went ahead and went 5 this way and then up 3. So that gives me the -3/5 slope. Graph that line. And then what I'm interested in is this intersection here. And it looks like it is at 1, -1 on my graph. And that goes along perfectly with my solution here, because I have this written wrong here because this is not negative. This is a positive 17 19ths. So the x coordinate is pretty close to -1. I can see that right here. The x coordinate is about -1. The y coordinate is +1. So my graph kind of goes along with my solution here. So if I had just graphed it, I would have estimated -1 1 for the solution to this system. And it wouldn't have been exact, but it would have been close. So that might have been good enough for whatever problem I was doing, but I might have needed an exact solution algebraically. Okay, so as you're doing this problem set, for each of the problems, what you want to be thinking about is how can I do this the quickest, easiest way possible. So I'm going to put up a few examples here and have you think quickly about which method you would use to solve it. We're not going to solve these, we're just going to quickly go through a few examples. All right, so here's the first one. Y equals 5x minus 19 and 3x plus 11 equals y. What method would be most efficient? All right, so notice that even though they're on, like, written on opposite sides, both of these are some expression is equal to y. You know, so I could turn this one around and it would be the exact same thing, right? This is the same as saying y is equal to 3x plus 11. So don't let that throw you. So what I would do on this one is I would be able to set 5x minus 19 equal to 3x plus 11, because both of those expressions are equal to y. So I think that would be the most efficient method for getting the x coordinate for this system of equations. Okay, let's do one more, or another one here. Okay, think as long as you need to, pause and think about this system. What method would you use here? All right, so hopefully you saw that eliminating the y terms would be the simplest thing here, and so I would add the left-hand sides, 2x minus 9y plus x plus 9y, and I would say that that's equal to the sum of the the right-hand side, 7 plus 5. When I do that, the 9y gets eliminated because I have opposite terms there, and I would get 3x is equal to 12, and x equals 4, and then I could go back and find out what y is up here. So elimination is the best method here. Okay, take a minute to look at this one. What method would you use? Which variable would you work on first here? Okay, so what I see is that if I multiply this second equation by -4 on both sides, then I'm going to have a 4x and a -4x that will be eliminated, and I can solve for the y coordinate of my solution. Okay, here's the last one. I want you to work on this one. Think of a solution and then work on it and see what you get. Okay, so you might have decided to take, let me use a different color here. If I multiply this first equation by -6, then I can eliminate the x variable. So I get -6x plus -6y is equal to, and then don't forget the -6 times the -3 would be positive 18. All right, and so then I can add my new equation to the second one, and I'm going to get 6x, let's go back to blue here. I get 6x plus 6y plus -6x plus -6y is equal to what? It's equal to 6 plus 18. All right, so I added the left-hand sides together and set that equal to the sum of the right-hand sides. But look what's happening here. Both of my variables are getting eliminated here, 6x and -6x, 6y and -6y. So I'm ending up with 0 is equal to 14. Not 14, 24. Is equal to 24, which I know is not true, right? So So you can think about, what is that telling me? Well, it's probably telling me that there is no solution to this system of equations. So I probably remember we've been asking ourselves as we do these, is there a solution? And so that might be really the most efficient use of time, although this didn't take very long, but given different numbers, it might. So let's look at, why is there no solution to this equation? Well, I'm going to put these both into slope-intercept form. So for this one, I'm going to get y is equal to negative x plus a negative 3 for this first equation. For the second one, I'll go through a couple steps here, and I'll get 6y is equal to negative 6x plus 6. And then if I divide everything through by 6, I get y is equal to negative x plus 1. So these are my two equations that I'm working with. So it's pretty obvious now why there would be no solution to this system of equations. Because what? Because the slopes are equal. The slopes both have negative 1. The y-intercepts are different. So these are parallel lines that will never intersect. So there is no solution. But I figured that out by using my elimination methods too. So this is not true, which tells us there's no solution to this system of equations. Okay, so that's pretty cool. All right, so let's look at what did we learn in this lesson. So this lesson summary is on your problem set, and it just summarizes the different methods that we have used to eliminate variables from systems of equations and find the solution. So you can look over that before you do the exit ticket and the problem set. All right, good luck with that. And I'm giving an extra day this week because these problem sets for 27 and 28 are maybe a little bit lengthier. If you don't need all the practice, you might be able to skip a couple of the problems. But make sure you at least look at all of them to be sure that you know how to solve them. Okay, good luck.